completely, yeah. So anyway, I think the recording, some portion is missed, but I don't think, I mean, too much of it. So just a quick repetition of what we discussed is based on the external electric field that we apply. The internal dipoles are aligned to give a net, positive and a net negative charge, which will appear on the plates of the transducer. And by the way, I'm using the word transducer or sensor kind of interchangeably and loosely, which maybe I should not. But I will explain the difference between a pure, a sensor and a transducer. So once we apply the net, a high electric field, as I said earlier, that the dipoles which were aligned in, which were pointing in different directions earlier, on the application of a high electric field, the dipoles align themselves in the direction of the electric field to give a net. And basically, you can see, right? These dipoles would have been pointing in different directions. With the application, they start pointing in the same direction, right? And even after we remove the electric field, even after the applied electric field is removed, the ferroelectric domains do not return to their initial orientation. So that's what we discussed also yesterday, right? And a permanent polarization remains. So basically, hopefully, like in this class or in this semester, whatever new subjects you are learning, it will impart a delta, an incremental change in your knowledge, and you'll a better person or a better engineer than you were one semester back, right? So similarly, once the electric field is removed, it's not that the dipoles go back to their initial messy position, but it remains kind of aligned, right? What is very important to note is the polling direction is therefore a very important material, aspect which we must be knowing when we are using this kind of a crystal, because without knowing the polling direction, when we apply, when we will be designing a system using the crystal, we need to know, right, in which direction our electric field should appear. And that's where the importance of the axis that we discussed for quartz. And by the way, again, I repeat, quartz is a naturally occurring material, whereas the perovskites can be synthesized, and the axis definition for perovskites are different. But anyway, we'll go back to all that discussion when we do some maths. So typical example of simple perovskites are barium titanate, again of the form ABX3, right, or lead titanate. And then there are more and more. There are multiple crystals, ceramic, which are synthesized, and a very commonly used one is something called PZT. This is a very commonly used material, and we will see in some of the transducer designs, right, that are done, how the transducers are realized using PZT. In certain polymers, piezoelectricity can be obtained by orienting the molecular dipoles within the polymer chain. It's very similar, just that instead of metal cations and anions, in polymers, the beauty of polymers, as I keep saying, is it is biocompatible. And PVDF is a very interesting family. Polyvinyl difluoride, if I'm not wrong, that's the full. Okay, I've written it here. Polyvinyl, I don't know if the spelling is correct, but PVDF is a very well-known material. And the main, while it has good advantage in terms of flexibility, because when we are talking of applications in medical, right, the material must be flexible, because only then we can do something with it inside the body, right? But the issue is the piezoelectric coefficients are much lower. So an active field of study that people keep pursuing is to develop more and more materials with better coefficients or better figure of merits. We have not discussed the figure of merits yet, but one active field of research is how do we make materials which will have higher piezoelectric coefficients, right? And so these are the different types of piezoelectric materials that are there. So ceramics, these are ceramics, and these are single crystals, polymers we have discussed. So yeah, I mean, this is just some general knowledge for us to understand that okay, we can realize this behavior or this phenomena with different materials. Okay. So we'll look into the PZT film fabrication a little bit. We'll not spend too much time, but you have to bear with me on this. And why we are going to look at PZT film? Because PZT is a very commonly used material, and it is composed of it actually we start fabricating PZT films with organometallic compounds as a starting point, and then the chemicals are dissolved. First, there is a solvent that is formed, and I have a flow chart to kind of explain this. And then a polymerization technique is used to produce a gel with a continuous network. The advantages, sorry, the advantages are homogeneity and mixing in molecular level, and low processing temperature and precise control. I mean, see, anything that we do right is in engineering is there are few things, few aspects or few good features that we target while we try to develop something, and one of them is controllability. The second one you can say is observability. Anything that is done right, if we can control the whole thing well, then it gives us a very precise realization of what we are manufacturing or fabricating, right? So one of the advantages of, why the PZT film is so commonly used, because it is, very, it has a very standardized way of manufacturing or fabricating. So this is what is done. So this is the flow. So we start with lead acetate trihydrate. This is the formula. You don't have to remember all this, but just I don't think I will ask you to remember, but it's important to know the flow. And then we have acetic acid, and both of them are mixed or refluxed at 150 degrees C. And then we add these guys, zirconium propoxide and titanium isopropoxide. We mix these guys in a nitrogen environment, and then for further processing at 80 degrees C, ethylene glycol and deionized H2O water. With these we create a stable solution. So first the solution is created, a gel kind of liquid is created for before we start depositing the film coating. So then with that solution, what we do is the solution is spun on at a very high RPM on a substrate, and substrate can be of platinum, titanium, silicon dioxide, or whatever substrate. So substrate we understand, right? It will be like a plate kind of a thing. So what happens is this plate may be rotated at a particular RPM, and we drop that gel. So when we rotate the plate, what happens because of the centrifugal forces, the gel will kind of spread and give a uniform kind of coating, right? So the hot plate is dried at 150 degrees C, and once it is dried, then again we heat it further to remove any organics that are left, and then it is annealed to densify the layer, and then we see whether we have achieved the desired film thickness. If the answer is no, then we go back again and repeat the process. And if the answer is yes, a final annealing is done at 700 degrees C for the final PZT film. So that's pretty much it about fabricating. We are not, as I said earlier, we will not discuss too much of fabrication because we are all electronics engineers, right? We are electrical engineers, so we while we know or will have a overview of the fabrication, but this is pretty much about it, right? Okay, so now this kind of material is actually very interesting, and we call them a smart material. And as I mentioned in some other context of this subject, understanding how the material actually works, it involves three domains, of course: electrical engineering, mechanical engineering, and material science, right? So when we talk of mechanical, properties of a material, right? What all things come to our mind? First, maybe we talk about density, right? Because we don't talk of density of a material in the context of electrical domain, right? So density, and then maybe we talk about mass. We talk about displacement. We talk about force. We talk about stress. Stress is nothing but force applied over an unit area, right? We talk about strain. We're going to look into the definitions. I mean, I'm sure you guys know the definition of all of these, but we'll have a quick refresh of them. And we talk of Young's modulus. Anybody remembers what Young's modulus is? You guys did have mechanics and in the first year, and hopefully you are aware of these terms, right? Young's modulus you're aware of, right? Anyone?
Yes, sir.
Okay, great. So, and then compliance. Have you heard of this term compliance? This you may not have heard in mechanics, or you are aware. So actually compliance and Young's modulus, they're related, and we'll discuss how they are related. But in the electrical domain, our electrical domain is probably much simpler in the sense that, we have very few fundamental properties which we deal with. One of them is voltage, and again, electric field is related to voltage. Capacitor, we talk of capacitor. I mean, these are the terms we keep using, right? We talk of dielectric permittivity, and we talk of electrical displacement, right? Which is related to polarization, right? So these are, the variety of terms that we used, and the reason I introduce these terms, I shouldn't say introduce, I kind of bring up these terms here because in the subsequent slides, while we'll be studying the material behavior and trying to develop a mathematical foundation for establishing their behavior, right? All of these terms will be used very frequently. So it's important to understand what each one of these terms actually mean. Most of them are pretty straightforward to comprehend, but few will have to kind of deal with a little bit more care. So, but before we do that, so what is a smart material? So let's define what is smartness, right? In material, when we say that this is a smart material, so let's say we have a material with dimension length L and width W, and we start increasing the temperature of this material. So because of the temperature, what we will see is maybe there is a change in the width and there is a change in the length, right? I've shown here as the change as delta W and delta L, but please understand this is just to show that there is a change. It doesn't show that delta W is a positive quantity or delta L is a negative quantity. But from the diagram, as we can see that delta L is positive and if delta L is positive, why should delta W be negative? Any guesses? Is there a reason that when we heat a material, the length elongates and the width reduces? Is there a reason for that? So very simplistically, we can say that, look, the total volume of the material remains constant, and based on that, it's a very kind of loose definition. So based on that, we can say while the length increases, the width should reduce. So what we see here in this process, that we have applied thermal energy, which is nothing but heat. We are increasing the temperature, which is resulting in strain. And what is strain? Strain is the change in the length. So my earlier length was L, and now after I apply the temperature, it's L plus delta L. So strain will be given by delta L by L. It's a ratio, right? So thermal energy is resulting in strain. But if the material is not smart, what will happen is the inverse will not exist. Meaning, if we were to apply a force and change the dimension of the material, we change the length from L to delta L, that would not mean that the temperature starts heating, right? So that is another way of defining. So far I was using the term transducer and sensor kind of interchangeably, but this is an important property. Important distinction, right? For what we mean by a transducer or the behavior, the phenomena of transduction. So what it means is the behavior of the material will be, it is interchangeable. It can happen from a mechanical domain. It can show from one domain, so thermal domain, to, let's say, a strain. Or in this case, this is the example that I've taken, that if we give thermal energy, we develop a strain, but the reverse is not true, right? So we can say that, okay, this kind of a material is not smart because there is no two-way transduction. But so far, whatever we have discussed about piezoelectric behavior, we have seen that if we apply a force, we will have an electric field, and we have not discussed the inverse yet in detail. That if we apply an electric field, there will be a stress or a strain developed. We have not discussed that. But from the definition of a smart material, a piezoelectric material does qualify as a smart material, right? That should be clear. So it is a smart material. So for a piezoelectric material, as we said just now, the electrical energy and mechanical energy are interchangeable, and hence it qualifies as a smart material. So, some kind of arrangement, transducer arrangement. So this is a piezoelectric material, and as you can see, this material has been poled. And what is the polling direction in this case? What would have been from whatever you are seeing in this diagram, right? What would have been the polling direction? The polling direction should have been this, right? Right? Because the internal electric field is in this direction. The internal electric field will always be opposite to the polling direction, right? That we discussed. So even though I've not shown the arrow, but you can figure out based on the charges that are shown here, what would have been the polling direction, right? So in this material, so let me just erase this. So in this material, if we apply a force and we have a potentiometer or a voltmeter, whatever you guys call it, and measure the voltage, we will get a voltage across the two terminals, right? So, and this we can call it as sensing, right? So this is the direct effect. I repeat, why this is sensing, because we are trying to sense a mechanical quantity is converted into an electrical quantity, and that electrical quantity can be read or it can be studied in a computer or whatever. So essentially what we have done is we have sensed the mechanical quantity that has been applied on the material, and the conversion is that has happened is from force to voltage, right? So now let's look at the reverse thing, what we call as the inverse effect. So in the inverse effect, the same material, what we do is we have applied an external voltage, right? So what will happen if we apply an external voltage. So if in this, or maybe I'll have another example to explain. So in this, right, you can see that we have applied a force, and because of which a positive voltage has developed, right? You can see the needle has kind of moved to the positive direction, right? So now if we do the reverse, if we apply an external voltage, so essentially when we, in this case, when we applied the force, what we would have done, we would have compressed the material, right? Meaning the material would have, let's say this was the material thickness before we applied the force, and after we applied the force, let's say it reduced, right? Because we are applying a compressive force, and it showed up as a positive potential. So now when we are doing the reverse, what do we expect this guy? Because it's a piezoelectric material, right? What will happen? Will this thickness, will this guy increase or will this guy decrease? What will happen, guys? It's the same. So let's say this same plate is on this side and the same plate is on this side. So when we applied an external force, compressive force, which resulted in a reduction of the thickness and created a positive voltage. Now what we are doing is we are applying the same positive voltage, right? What do we expect the thickness to become? Will it increase or will it decrease? Any guesses?
If initially it has decreased, then now also it will decrease.
Now also it will decrease, right? We'll have, yeah, coming in, Shubham, please go ahead.
Yes, sir. I just said that if initially while applying compressive force we get a positive voltage, then if we supply a positive voltage, then it should decrease.
Yeah.
Like
Okay.
compressive strain.
Yeah. Shubham, one thing. So just one piece of advice to all of you actually. So English is a very funny language, right? And but the problem is we deal with English. So, but in engineering, right, we have to be very careful when we are using terms, right? I mean, all of us do the mistake. For example, Shubham used the term initially, right? But if you see here, so the term initially is associated with time, right? But in this picture that I'm showing in both the pictures, it's a snapshot, it's a picture. The time is not a variable here at all. So probably the right way to put is the right way to answer or say with all the correct terminology. I'm not saying Shubham doesn't know it; everybody knows it, but we have to be just careful of the choice of words. So what the answer would be, sir, in the first picture or in the first diagram, if a compressive force is resulting in a positive voltage across the terminals as shown, so then in the second picture, if we are applying a positive potential across electrodes, then we expect a similar mechanical response, which means the thickness will reduce. And I'll talk about it a little bit more in few of the next few slides. So what we see is the thickness, which is the y direction. I mean, in this case, it is y-axis. The dimensions have reduced from y to y minus delta y, right? And this we call as actuating, which is essentially the inverse. So from force to voltage, in the first case, we went from force to voltage. In the second case, we're going from electrical to mechanical, voltage to strain, right? So the first one is the direct effect, and the second one is the inverse effect, which is what we had kind of talked about, right? Now let's make things a little bit more interesting. We'll do, as I said, right? We'll kind of get into more and more maths. So let's say we have a material. So this is clear, right? This material is kind of tied to it's glued. It's glued to a piece of, whatever, maybe a wall or whatever. And the cross section has an area A. the length of this bar is L, right? So if we apply a force F, we are applying a tensile force F. So we know, right? If we are stretching a piece of material which is glued, what will happen? The length will increase, right? Because this guy is glued here. Effectively, we have an opposing. I mean, we have the force on this side on the opposite direction, right? Essentially, we are stretching the material, because of which the length changes from L to L plus delta L, right? So we'll come to it. I probably should have used the animation one after the other, but let's go through each equation carefully. So we know from if we treat this material as a spring, if we treat this material as a spring, and we have applied a right, and the spring has moved from an initial equilibrium position. So let's say this is x equal to 0, and the spring has moved to, let's say, whatever x equal to x. So then the force that is applied is proportional to the displacement that has happened. And so this we know, right? The spring equation, F equal to kx, we know, right? So this is the same thing that I've written. The first one is nothing but the k is the spring constant. We know this, right? And what is stress? So the area that is shown here is A. Stress also we know is sigma. And by the way, I'm introducing new notations here, because in the subsequent slides we will start dropping the mechanical notations, and we will start using the electrical notations more and more. So the stress, which is shown as T, I mean, it is denoted as T by the letter, is nothing but force applied per unit area. And the strain is nothing but, in the mechanical world, the mechanical guys, they denote it by epsilon, and we will be talking of strain with the letter S. We need to remember this, because in the subsequent equations, whatever we developed, it will be all in our electrical terminology. So T is equal to Y times S. So, or in other words, so this we know, right? Sigma is equal to Y times epsilon. So this equation we know. What is this equation known as? Any one of you guys remember? Any one of you guys remember? This equation you would have seen, right? Sigma is proportional to strain, and that proportionality constant is given by the Young's modulus, right? So this, I think, termed it as a Hooke's law, right? So there is this is a linear equation, and why is it a linear equation? Because if we, so you understand the properties of, I mean, when we properties are linear, right? So this is definitely a linear equation, right? Is equal to y epsilon. So what we do is we are trying to get a relationship of the spring constant k and the Young's modulus. That's our goal. That's where we are going. But let's do this step by step. So this is a fundamental mechanical law coming from the mechanical folks. Is T is equal to Ys. Now, if we multiply both sides with area A, right? So then this becomes force F, right? And strain has been replaced with delta L by L. So this is Young's modulus. And then to here, force is equal to K times X in this form, right? So by inspection, what we can see is here and here, we can see K is equal to Young's modulus times A times L, right? So this we will kind of remember. And the compliance, I think I asked this question, what is compliance? So compliance is actually opposite of Young's modulus, or what is stiffness, right? So let's look at this equation again. T is equal to Y times S, right? Or S is strain, right? So higher the Young's modulus, for the same applied stress, what will be the change in the material? The change will be lower, right? Meaning higher the material modulus, Young's modulus of the material, with the same force, we will get a lesser strain. So that means the material, we can say the material is very stiff, right? Like for example, I mean, we use this in our common day-to-day term also, right? For example, let's say I set some rules for the class, right? And being students, it is expected that you will comply. But few of you may not comply, right? Because, so inherently, let's say a few students may be very stiff, or in other words, they don't have regards for rules, right? Or they don't want to comply with whatever rules have been set, right? So Young's modulus is effectively stiffness. We can think of it as stiffness, and elastic compliance is the inverse of that, right? So basically, compliance means if you are if you are applying a force in this direction, what are we trying to do? We are trying to stretch the material, and if the material has higher compliance coefficient, what will happen? It will follow the instructions that it is being given, and in this case, the instruction is that is being given to the material is, hey, why don't you stretch yourself, right? And if the compliance coefficient is high, the amount of deformation in the direction of the force will be more, right? Basically, it is complying to the external information that we are giving, right? So we are going to denote the compliance coefficient, elastic coefficient by small s. It's a little bit funny s that I've drawn, but I had no other option because running out of letters. So compliance is also denoted by a small s, and it is inverse of Young's modulus. So a lower stiffness means higher compliance. So straightforward, right? So the same equation, K is the spring constant K is equal to Y times AL, can be written as AL times small s, right? So it is so basically the spring constant is proportional to the area, right? It is inversely proportional to the length of the material and inversely proportional to the compliance. So, any questions up to this point? I think I've tried to make it simple, right? No questions, right? So it is understood, the definition of compliance is understood. And so is Young's modulus, right? Okay. So, what happened? Yeah. So now, again, taking the same example, we have applied a force, and because of the application of the force, the change in length, there is a change in length that has happened from L to L plus delta L, and the width has changed from W to W plus delta W, and we have shown the x-axis and the y-axis. And so the Poiseuille's ratio is given by the strain in the y direction divided by strain in the x direction. Please note there is a negative sign here, and there is a reason why we introduced the negative sign. The reason we introduce the negative sign is, see, for example, when you are applying a force in this direction, as we discussed earlier, this material will elongate. But because the overall volume or overall mass remains the same, right? Assuming that it doesn't change too much and all that stuff, there are assumptions. So when the length increases, the width reduces. So the strain, a positive strain in the x direction will create a negative strain in the y direction. Now, when we are taking a ratio, we are saying that it's a ratio. So we are saying that it's a magnitude. In order to ensure that it remains a magnitude, we introduce a negative sign so that when epsilon x in this case is positive, greater than 0, epsilon y will be less than 0. So once we divide, this term is actually a negative term. So to take care of that, we have introduced negative sign before that. So this is Poiseuille's ratio. And again, these guys are going to come into picture later. So we are just setting the definition so that once we see the equations, we will be able to relate to these fundamental relations, right? And now we go back to the same word polling, right? And we have discussed, how a dielectric, a dipole is created. So we have, I think, do I have a diagram? Yeah. So we have a positive charge plus q here and a negative charge minus q. We have a distance d separating them. So the dipole moment is a vector which points from the negative charge to the positive charge, right? So this is a vector. The dipole moment is given by q multiplied by q times d. D is the displacement or the distance vector between the two charges, right? Discussed all about this, why polling is needed and charge. The overall net charge is 0, but there is an effective dipole that we have discussed in detail, right? So I'm just repeating these things so that it kind of reinforces what we have discussed. And this also we have clarified the direction of the electric field and the dipole moment, the external electric field. The direction of the external electric field and the dipole moment, how they are related, right? So in this case, again, the internal electric field and the polling direction, they are going to oppose each other, right? Um, yeah, so I think that's pretty much, I think this is a good point to break. Let me see. Do we want to? Yeah, I think we'll break today for now. And guys, on the lab, right, I'll send you an email. So the lab class will be also online. It's not a very good thing, doing lab classes online, but we don't have any other option. So we are working out the assignments that will be given to you online. And by the way, from these lecture classes that I am taking, I will be giving you assignments pretty soon. And there will be weightage on the assignments in the class. So you will need to submit the assignments. I think there are a few more classes before I give you the first assignment. So the lab work will also be in an assignment format, and probably you will have to presentation. I'll see how to kind of we'll probably make groups of students, and you'll have to make a presentation of what the experiment that you did or simulated, studied or learned, right? So the lab will start from next week, not from this week, right? So that's pretty much for today. We'll stop here today. It's a good point to break. And please note, we are just scratching the surface of the subject. Things might be looking pretty easy, and it is easy. And the goal is to make it easy. But it's very important we set the context clear, meaning whatever we have been discussing, the terminologies, the notations, even the assumptions that we are making should be very clear, because without that, the subsequent portion of the discussion is going to become pretty cumbersome, right? So any questions, guys, so far? I'll stop here. So one advantage of, I think, I'm not sure in many of your other courses also the subject matter is taught using PPTs, or it is like kind of drawn in hand, or how are other courses mostly taken? I mean, do you have PPT materials to support you, or how is it? Because I'm doing it with PPT just to ensure that we save time, and also kind of the flow is kind of I mean, once I make it in a PPT, right, the flow becomes, I would say, more lucid. So hope that this is making sense. The PPT flow of it's not so easy because you have to spend time in creating the material and in creating the animation. It's not just a copy paste, but yeah, hopefully that this is making sense to all of you guys. We'll see in the next few lecture classes. Any questions? Please drop me an email.
Sir, I
And
have a
yeah,
question.
Shubham, you want to say something?
Yes, sir, I have a doubt. If we say that
Yes.
this piezoelectric material is having a non-zero dipole, then this dipole is appearing due to polling, or we do polling to try to remove this non-zero dipole?
No, it is appearing due to polling. Meaning, in fact, polling is done intentionally. So basically, it's like this. In fact, what I was thinking yesterday, right? When I told you that, going back to the perovskites, right? And I asked you a question, and some of you kind of opposite to what I was expecting. And that was again my failure to kind of put the thing in the right context. But let me go back one second. I'm just trying to go back to the slide of perovskites, right? I give you a piece of here. So let's say I give you a piece of crystal, right? And say this is a piezoelectric material, Shubham. Why don't you create a transducer out of it, right? And as we discussed earlier, the piezoelectric behavior will manifest only applying the force in certain directions, certain axes, right? So if I give you the material, it's like a small, let's say a cubic box. How will you find out that okay, this is my x-axis, this is my y-axis? How will you even do that in the first place, right? Because I have not told you that this is the x-axis or the y-axis, right? But let's say somebody has shipped material to you, and you have to figure out, right, which is what. So one of the advantages of having, one second, there's a, one second, please, just give me 1 minute, I'll be back, one second. Yeah, so going back to that discussion, so if I give you the piece of material, how will you find out that, okay, I need to apply the force in this axis, or I need to apply my external battery in this axis, right? So you can say, okay, sir, why don't you could have marked, you can give, you can write it on a piece of paper or maybe mark it on the material itself, right? But the best way to actually, do it is to have some residual electric charge, right, in the material. So what you can do, right? Let's say I've given you a cubic material, you can take a voltmeter and put the probes on two sides of on the of the material, opposite sides of the material, and on only a certain opposite sides, right, you will be able to measure a voltage across it. So then oh, okay, this is the axis, this is my electrical axis, and this is where I will need to apply the force so that I'm able to get the piezoelectric behavior. So polling, to answer your question, so polling is done. So if you look at this, right, what has polling in this case, right? Without polling, this guy, this B cation, is sitting right in the center, right? Without polling, forget the temperature for the moment, forget Curie temperature, right? Without polling, this is right in the center. But what the polling has done, so basically there is no effective dipole, right? What the polling has done, it has moved this guy upwards and created a net charge on that, right? So, but you can say, but how does it matter? Why do we need a net charge in the first place, right? Because anyway, if we apply a force, this guy will move, and anyway we'll get a field. That is true, but how will you get to know which direction you need to apply the force, right? I mean, the person or the company which is manufacturing the material, it needs to show you, or it needs to tell you, right? Hey, that this is the axis that you need to be interested in, right? So that is one reason you can think of why pooling is done, to create a net charge. And you know, okay, this is my axis, all my force and electrical measurement and blah, blah, blah needs to happen with respect to this. Is this clear, Shubham?
Yes, sir. Yes, sir.
Okay. Any other question, guys? Yeah, don't worry. I mean, I'm not sure. Sometimes subjective material can be boring, but don't worry. There are enough maths coming up. Okay, guys. So we'll call it a day for today, right?